So now talk about actually concretely using mathematical induction. And I like to use these following 4 steps, although one of them is pretty trivial. First, I'm going to identify my propositional function p of n, where what I'm trying to prove is for all n, p of n is true. Then I'm going to prove my base case, which is prove that p of 0 is true. Then we're going to announce our induction hypothesis that p of n is true for some n at least 0. And using p of n, we're going to then prove the p of n plus 1 case. So here is a statement we can prove using induction. Let a n be a sequence defined as a of 0 is 5, and for n at least 1, a of n is equal to a of n minus 1 plus 3. So I have this recurrence relation definition of my sequence an. I want to prove that I have this closed form of my sequence where the nth element of my sequence is equal to 3 times n plus 5. So the 0 step, identifying the p of n, where this is my goal statement, this is my p of n. The sentence a of n is equal to 3n plus 5 is my nth sentence I want to be true. I want that to be true for all n at least 0. I want to start by saying I'm proving by induction, and now I'm going to use step 1 to prove my base case. My base case n equals 0, well I know that a0 is given to me as the definition is 5, and that's 3 times 0 plus 5. So this sentence does hold. P of 0 is true. Next step is I'm going to announce my induction hypothesis. So I've now written my induction hypothesis, and I've even used the phrase induction hypothesis to explain what I'm saying. For some n, I'm going to say that an is equal to 3n plus 5. So now I want to prove my last step. I want to prove the p of n plus 1, which means I need to start by saying, well, a of n plus 1. I know that this is equal to a of n plus 3 because that's what my recurrence relation says. And this works because n plus 1 is at least 1. And that's an important thing. It's a very subtle point, but it's really important that I can actually use this recurrence relation because n plus 1 is actually a number at least 1, which means I can use this definition here. But now I want to actually use my previous statement. I know a closed form for a sub n. So by the induction hypothesis, a sub n is equal to 3n plus 5, which means I have that a sub n plus 1 is equal to 3n plus 5 plus 3. But then I can say I have 2 3's here, so I have 3 times n plus 3 times 1, and therefore I have what I get is 3 times n plus 1 plus 5, which verifies our statement p of n plus 1. Just to finish up, I want to actually conclude that because of using induction, I get this statement for all n. And therefore, I have completed my proof, and I have verified this statement.